Welcome to today's episode. We have the pleasure of hosting Thomas Jam Pedersen, whose unique background in software engineering and energy consulting offers a fresh perspective in the field of energy. As one of the co-founders of Copenhagen Atomics, Thomas is at the forefront of advancing energy technology, particularly in the domain of molten salt reactors. Join us as we delve into this interesting topic and Thomas's journey, his deep insights into nuclear energy, and the groundbreaking works his company is doing to redefine the energy landscape.
Hey guys, welcome to the podcast. Today we get something pretty unique, which I'm actually pretty excited about. So we're talking with Thomas Jam from Copenhagen Atomics, and it's something probably very different than we've ever had on the podcast before, because Thomas actually has built something really unique, which is actually dealing with nuclear power. So Thomas, do you want to tell us about yourself and your company and let us know what you've got?
Yeah. So I'm an engineer by training. I've worked with a lot of different systems for 2 decades, and then I stumbled into this project. I'll get back to what that's all about. Originally, I was an electrical engineer, but I worked mostly with software. I worked for Nokia back when that was sort of the #1 technology company in Europe, and since then I worked for a number of startups, and we tried to start also another startup in the energy sector, and actually that was energy storage, but it never got off the ground. But then I stumbled across this idea of thorium energy, and it took me almost 2 years from I heard about it first time till I really started studying it more carefully. And basically, the thing that intrigued me in the beginning was there was this images on the internet about a ball the size of a golf ball, roughly. Can supply you with all the energy you need for your entire life if it's made out of thorium. And I mean, not just the electricity you need at home, but everything, including transportation and your share of homes and houses and hospitals and everything, roads and so on. So I thought that's amazing. If you can get all that energy out of this little ball, like how do you actually get it out? Like by then I knew that thorium is a metal. It's one of the elements in the periodic table. And I knew you get it out of the ground by doing mining, and I also knew that it was not very expensive. I mean, there's lots of thorium in this planet, and a golf ball size costs roughly $100. So the question became like, how do you actually convert that metal ball into energy, and why are we not doing it and stuff? And so many years went by, and I met some really smart people, and we started sort of collaborating and exchanging ideas of how we could potentially build a nuclear power plant, because it turns out you need sort of a nuclear reactor to convert thorium into energy. Thorium has been used in all the sort of classical nuclear reactors, so we know that it can be used, but it doesn't have any economic benefits in classical reactors because of the way they work. You basically need a new type of reactor to make thorium energy economic. And those reactors are called molten salt reactors, and I learned a lot about those more than 10 years ago, and started going to international conferences about it and read a lot of stuff on the internet about it. And there was an experiment back in the 60s where they ran one of these molten salt reactors for 5 years in the States. I've then been lucky enough later to visit that site and see it up close. But in the beginning, I was just reading about it and figuring out how it would work, and I realized it's not that difficult to build. I mean, it's not easy, but it's also not impossible. It's not like fusion that is super difficult and you need billions of dollars. This is sort of doable. And I was still wondering why nobody's doing it. And then, like I said, I met these other guys. We have 4 people who started Copenhagen Atomics, and some of those were chemists, and molten salt had experience with molten salt chemistry and stuff like that I didn't know about. So yeah, we decided to start a company, and it was sort of in the beginning, it was sort of a long shot, right? Because we 4 guys in the garage saying, okay, we want to build nuclear reactors. and then, it's a long story, but essentially through those first couple of years, we realized that it would actually not be super difficult to mass manufacture these reactors on an assembly line in a style where you could make 1 reactor every day. And these reactors can make lots of energy. Like it's on a whole other scale than classical nuclear energy. And also the waste that you produce in the end is much less problematic than the waste from classical nuclear reactors. So we like that a lot, and therefore we called the reactor that we designed the Copenhagen Atomics waste burner. And essentially, it's able to take it's able to mix thorium and nuclear waste from classical reactors and run on that and create a lot of energy, and then reduce the amount of time that waste from the classical reactors have to be stored. So basically, the waste coming out of our reactor only have to be stored for 300 years. I mean, that it still needs to be taken care of and handled in a safe way, but it's much easier to handle something for 300 years than for 100,000 years. So that's the sort of the short story of how we ended up here. I would love to go into more like technical details, or maybe more details about how it works, or what we want, where we want to sell it, and stuff like that.
Yeah. So it's because I think it'd be good to explain to people listening that when you think of it, I think of a nuclear reactor like watching The Simpsons back in the day, and these big, crazy, just take up acres and acres of space. And so your reactor fits in a shipping container. So it's a 40-foot shipping container or a 20-foot shipping container?
Well, so we built different models for testing, and we have built one sort of small test unit that fits in roughly a 20-foot shipping container. But now we're building bigger ones, and the commercial reactor, sort of the one that is going to make energy for people, fits in a footprint similar to a 40-foot shipping container. It's a little bit taller, and it's not a standard shipping container. The walls are much thicker, and it has some other features. But that's sort of the size of it. That's a good reference.
Totally. And so with that sort of size system, like like there's a lot of in Australia here, like, because we do off grid, and there's a lot of mining companies these days are buying. It's interesting. I was talking to a guy the other day, and so a lot of the mining companies are calling them solar generators, and I was like, "What do you mean a solar generator?" And they're like, a solar generator. And like, to me, have you seen those little EcoFlow little mini solar generators at like $1,000, and you take camping and plug your fridge and stuff into?
Yeah.
That to me, in my head's a solar generator. And after talking to this mining company, they're like full on off-grid systems, 100 kilowatts of panels, batteries. That's what they're considering a solar generator. I was like, okay. and to me, it's just off-grid system. So, and so a lot of the guys are putting shipping containers up, batteries, inverters, and panels, and the panels can come off the container. So if we're comparing to that sort of off-grid system that we would sort of do, what sort of energy can you get it and provide out of a 40-foot shipping container using this technology?
Yeah, so it's our those commercial reactors, they would provide 100 megawatts of thermal energy, and that's roughly, you need to convert that heat into electricity in order to compare. And in many systems, you would have sort of a conversion rate of 42%. So basically 42 megawatts of electricity would come out of one unit. And in most cases, we would make power plants where we put many units at the same site. So I mean, you could just put more and more units, and then of course you get more and more electricity.
Yeah. So you're saying 42 megawatts. So is that like the current the power we could pull at any one time?
Yeah, it's so that it's base load energy you just run 24/7 for a number of years. So I should say that ideally we would like to build power plants where you get a license to run it for 50 years, and the building and everything is dimensioned for 50 years. But of course, some of the things inside needs to be replaced more regularly. And for example, that container that I talked about with the reactor inside, that is a sealed unit, and because of it's very expensive to try to refurbish that or repair it. So it's actually a better deal to run it for example, 5 years, then decommission it and bring in a new one, and then move all the salts and other expensive things, heavy water and so on. That is pumped from the old unit over to the new unit, and then you continue to run on the new unit. And that also means that sort of all the technology is upgraded every 5 years. So your software and your sensors and your pumps and heat exchangers, everything has sort of the latest and greatest technology. You upgrade every 5 years. And we found that that's actually the most economic way to do it, rather than try to replace some of the components inside, or refurbish it or something.
Yeah, interesting. Yeah, no, definitely. Because like one of the biggest problem with nuclear power plants and where every few years they have to top up the fuel source. Is that right? With a traditional nuclear power plant.
Yes, correct.
So they've had shutdown times, and so they're literally got to use some other energy source to keep everything powered while they shut them down and load them. And so with your systems, basically, you can do it live. Basically, is that right?
Like each unit still have to be down for a number of days. Let's say 2 weeks. Be down for 2 weeks when you swap over to the new unit. But ideally, there would be many reactor units at each site. So let's say one of those projects we have in Indonesia, there's 25 reactors always live, and then there's a few extra ones in sort of backup. So I mean, if you have 24 online or 25 online, and you need to swap one of them, then I mean, obviously you only go down by 4% power while you swap that in and out, and so that's a very it's like it's always on. There's always reactors running, so nobody would even notice that you're swapping from one to another.
Yeah, totally. So so for smaller communities, it'd probably be better off having a few smaller systems that they can swap between. I'll give you an example. I did a consultation in the Daintree in Australia, and it's a very very controversial up there with the energy system, because they've never been looked after. They've got no power, and everyone just sort of had to sort themselves out. And it's a challenge because it's really hot, humid climate. We get cyclones. So solar panels up there, and because everyone builds their houses within the rainforest, so there's lots of shading. So solar panels are a bit hard. You don't want to put them out in the open areas because the cyclones just come and take them away. So a lot of the Daintree, the pub up there is a great example. So the hotel, where food, restaurant, bar, it literally has a 50 kVA generator that runs all day, and then overnight, to save fuel, they flick from the 50 to the 14 because it runs a pub plus it runs a village, so that power is for everyone. So I could see with something like this, would be really ideal for someone like where solar just doesn't work because of the risk of the cyclones blowing the panels out that are out, away from the rainforest. And then, literally, they've just got that ongoing consistent power. And from renewables, not running diesel generators, which would definitely makes sense there. So, okay. So, mate, tell us a bit more. So, I know, so the Oak Ridge experiment basically in the States, they did some testing on molten salt. So tell us a bit more about the difference between a traditional reactor and a molten salt reactor, the path you guys are going down.
Yeah. So the big problem with all the classical reactors we have all over the world is that when you run them, they generate something called fission products, which is basically the waste product from the when you burn the nuclear fuel inside of it. I should say that in the nuclear industry, we call it burning the fuel, but it's not burning like your fireplace at home with oxygen that is making a flame. It's basically a nuclear process that converts uranium into fission products. And when that is done, it creates a lot of heat, and that heat is used to drive turbines or whatever. So this generates fission products, and those are the waste products. In all the reactors we have all over the world today, those fission products are not removed. They stay inside the reactor core, and eventually they eat up all the neutrons, and this means that the reactor has to stop. I mean, it long before, when you've used sort of 1 or 2% of the fuel that you put into it, it cannot run anymore because these fission products builds up, and then you have to discard all the fuel, including the 98% that was never burned. And then you put in new fuel, and you run that for a couple of years until you burn 2% of that, and then you have to unload. So it's a crazy inefficient system. It's just unimaginable how inefficient it is with the way it uses the fuel. And that's where molten salt reactors are completely different, because now you have a liquid fuel form, and you can actually remove those fission products online while the reactor is running. And I mean, the simplest way to do that is some of the fission products are gaseous. So they are xenon or krypton or some of these gases that are that doesn't, they are inert gases that doesn't react with anything. So they will just bubble out of the salt like, soda pop, bubbles, CO2 bubbles out of soda pop. So a lot of those are super easy to remove because they basically remove themselves. And some of the other efficient products are more difficult, and you have to remove those with different means of chemistry. And to get a really high performing reactor, you would want to remove all of them. But of course, I mean, realistically, you don't do that with the very first version. With the very first version, you just remove all these gases that are super easy to remove. And then a little bit further down the line with version 2 and 3 and so on, you remove more and more of those fission products. And some of them are much bigger problem than others. So, I mean, ideally, you want to remove those that are capturing the most neutrons first. But again, and then the chemistry is also, some of them are chemically really difficult to remove and others are quite easy. So you have to look at all that chemistry and see how can you remove those. And we have been working on that for a few years, and we're not able to remove all of them yet. But of course, we know that, us humans, we figured out many years ago how to separate all the different elements in the periodic table. So we know the chemistry of how to do it. The question is just, can you do it automatically inside a reactor where everything is radioactive? And of course, it's a little bit more difficult. And also, sometimes when you do chemistry, you have sort of a waste stream, or that from mining as well, with all the tailings and stuff. So of course, inside a reactor, you want to generate as little waste as possible. So of course, that goes into the consideration of which of these elements you want to remove first, and which you sort of postpone till the next version or next version. So that's basically why molten salt reactors are completely different than all the classical solid fuel reactors, is that you can remove those fission products, and therefore you get a much higher efficiency in the way you use the fuel. And then on top of that, when you want to use thorium, if you put thorium in a blanket, sort of you can imagine you have the nuclear reactant in the center of the core, and then you have a thick blanket around that made out of also a liquid salt, so a thorium salt. So it basically, think of it as 0.5 meter thick tank on the outside of the reactor. And when the neutrons try to escape from the reactor, they will fly outwards, and then they are captured by that blanket. And if you design your reactor correctly, then those neutrons will convert the thorium into new fuel, which is called uranium-233, which you then put into the core, and then it sort of continues to breed its own fuel from that blanket, and then run in the center of the reactor. And this is something that is possible with molten salt reactors, but it's completely impossible with solid fuel reactors, which is all the types of reactors we have everywhere in the world today. And this has been known for many, many years, since the 50s. But I mean, it was not super easy. They made it work in the 60s, but they didn't have computer simulations back then, so it was really difficult for them to optimize it. Also, they didn't know all the chemistry we know today, how to remove the fission products. And thirdly, we have some new materials today, new material science that they also didn't have back then. So there's a lot of things we've learned since the 1960s that makes this possible today, which would have made it really difficult or hard to do in the 60s. So they sort of showed that it worked, but they never got to a sort of a full-blown commercial reactor. And this is what we're trying to do in Copenhagen Atomics. And of course, we want to do the whole thing with the thorium blanket and remove those fission products to get very high efficiency. And I mean, maybe not the first version, but once we've built a number of versions and learned how to remove these fission products, we believe that we can get to a situation where we can get 100 times more energy out of the same amount of mining as the classical reactors. So if you mine 1 ton of material for the classical reactors, or you mine 1 ton of material for our reactor, then we can get 100 times more energy out of that. This is really mind-blowing, because normally in the energy sector, whether it's solar panels or something, you normally see improvements of 1 or 2 or 5% every time there's a new generation or a new version of that technology. I've never heard in my whole life, I've never heard of some new technology in the energy sector that improved by a factor of 100 over the previous version. And this is the potential of this molten salt reactors in combination with thorium, because you cannot get such a big improvement if you were to run it on uranium. You have to mix it with the thorium to get those high improvements.
Yeah, it's interesting that a couple of presentations I've watched that you've done in the past. And to me, one of the biggest things that I really care about is embodied energy, and I think there's a really good graph that you showed on one of your presentations about all the mining and all the materials used to make solar energy compared to the mining and everything that uses to use your reactors and use thorium. And it was just crazy of how much materials were required to make such little solar energy compared to how little of products required to mine to make so much energy with your product. So can you tell us a bit more about that?
Yeah, this is how I got sold, basically. When I saw that chart, 15 years ago, maybe more like 12 or 13 years ago, I was like, is that really true? I want to look into that. And then I did a lot of looking at different energy sources and how much energy is needed to get oil out of the ground or coal out of the ground, and then how much energy do they create, and how much energy goes into making all the steel and concrete for a power plant, whether it's a nuclear power plant or coal or oil power plant. And of course, being from Denmark, we are very famous for wind energy. And I actually, early on, I invested some of my money in some of the wind turbine companies here. And I also looked into that. And you might know today, some of the really big wind turbines, they need more than 1,000 tons of steel for one turbine. That is a lot of steel. And if you go look at how much energy is needed to make steel, it's a lot of energy. And of course, also usually they have a base of some sort made out of concrete. And again, concrete also takes a huge amount of energy. So when you start to calculate, okay, how much energy goes into the all the wind turbines we've ever built in the world, and how much energy has come out, it actually turns out, because we're growing the number of wind turbines all the time. So it actually turns out that it's almost the same amount of energy that we get out of all the wind turbines as we have put in to build them. And the reason why it might be a good idea is because we keep on growing the number of turbines. So eventually, in 20 or 30 or 40 years, when we stop growing the number of wind turbines, then there will actually be some energy for the humans. But as long as we keep on growing at this fast pace that we've done for the last 30 years, all the energy that the wind turbines are producing goes into making more wind turbines. There's never been any energy for the humans. And I would actually even argue that we even have to supply some of that energy for building them from coal and oil and gas. So it's basically CO2 negative so far. But of course, we're building up capacity. So someday when we stop building wind turbines, then there will be lots of green energy for the people at that point.
Yeah, totally. Yeah, it's to me, like, self-sufficient. That's always been my thing. That to be self-sufficient, you need to give the system more energy than you take from it. That's sort of how I think about it. From electricity, energy, well, just everything in life. To me, I always think about the world as one big fuel tank. And it's another thing as well that I do a lot of presentations and talk, and I always ask people at the end of my talk, if you were going to go do one thing today to make the biggest impact on the world, what would it be? To save energy. And I might ask you that question. So if you were to go, do one thing today to make the biggest impact to reduce your energy consumption on the world, what would it be?
I mean, obviously I would prefer to make more energy at low CO2 and low cost, rather than trying to save my way to a better situation. That would be my choice. But if you tell me you have to save somewhere, that's difficult to say, but obviously one of the things is flying on airplanes that require a huge amount of energy. Now I live in Denmark, and we actually have houses here that are really well insulated, and we don't use air conditioning very much. But in most countries of the world, the houses are not very well insulated, and they either use heating or air conditioning, and that is, I think, one of the places where it's easiest for most people in the world to save money is to put more insulation and try not to cool it down to 17 degrees inside when it's 30 degrees outside. I mean, be more reasonable with this heating and cooling, and if we built the houses in a more sustainable way, that we can also think about how we build them so that less energy is needed, both for light inside, like electrical light, but also again for the heating and cooling and water and everything. So I think there's lots of savings on housing. And I also think, I mean, I also drive a pretty big car, but it's sort of when I was younger, I always used to bicycle. Of course, it's more healthy for yourself because you get some exercise and you get fresh air. And it's actually a nice way to transport yourself around if you live in a place where it's not like super cold or super hot. But I think many more places in the world we could use bicycles, and we could maybe change society a little bit so that you had a shorter distance to the shops and the place you work and school or whatever. So I think, I mean, it wouldn't be too difficult to double the amount of people in the world that uses bicycles every day, and that would have a huge impact. And it's a little bit, it's not great to see millions of cars that weigh 2-3 tons just sitting in traffic, not moving. I mean, that's a waste of people's time. It's a waste of energy to haul those 2 tons of material around. And usually there's only one guy in each car. So like that's a waste of energy. But I have to admit that I also do that. I have the distance from where I live to where I work is like half an hour in the car, or almost. So it's a little bit difficult for me to go by bike, but I can do it sometimes if I want.
Yeah. But it comes down to bad design, and there's a lot of that. Like, in Australia, we have really bad designing houses. So, we use a ton of energy to heat and cool. Energy's been cheap for so long, that sort of stuff. But so when I do my talks and what I talk to people about, the most energy intense thing that you will do every single day is actually eat. So by growing your own food is one of the best things you can do to reduce your energy consumption on the world. Grow your own food, harvest your own water is another thing. In Australia, the amount of energy is used to pump water around. So having a rainwater tank, that can really help out. And then the last one I always say to people is catch public transport. It's one of the 3 biggest things that you can do to reduce your energy consumption. And everyone always thinks when I talk about energy and solar, install solar and batteries, but it's always like, just grow your own food, because that's the most energy intense thing that we do. And I suppose one of the reasons it's the most energy intense thing that we do is because of the ammonia that is used in fertilizer stuff to grow food. So tell us a bit more about doing some research that, with your products and how it can help the ammonia industry.
So that's one of the things that most people don't know, is that if you look at all the food we grow in the entire world and the area that we need to grow that food, I mean, if we was not using ammonia, if we were not use pump water for irrigation, then we would only be able to produce half as much food in that same area as what we do today. So you could say half of the world's population, 4 billion people, basically would not have any food if we didn't use ammonia and pump water or irrigation. So that's how important ammonia is. I mean, it's not something we can just shut off. It's sort of really important for the for the supply chain of food in some sense. And a lot of that's one of the scary things in most big cities in the world, and more people live in big cities. There's sort of a just-in-time food supply. I mean, those big cities only have enough food for a few days for the population. So if you cut off the food supply, a few days later, they will start running out of food. And in a week or two, people would just be dying because anyways. So that's sort of a scary thought. But and that this makes ammonia really important. Not only like, of course, we're farming the food in most countries in the world, and therefore now with the sort of the energy crisis and gas high gas prices last year around this time, a lot of countries start thinking about, oh shit, I mean, we need to make sure that we have not only energy supply for, gasolines for our car or whatever, but we also need to make sure that we have ammonia supply so we can grow our own food, that we're not reliant on Russia or some other place to make the ammonia that we need to grow the food for our population. So actually many countries have started looking at, how can we make security around the supply of ammonia, and given it very high importance compared to supply of other things like concrete or whatever. Because that's another thing people forget. In the Western world, at least, we consume so many products, and we're so used to just going to the shop and picking it up and buying it, and we don't think about where it came from. But all those products that we've consumed all our lives, they're all made in factories, and those factories are made out of steel and concrete and aluminum and stuff like that, and those materials need a lot of energy. Steel, concrete, and aluminum use a lot of energy to make those. So even though maybe some of the products we consume doesn't use a lot of energy to make them, the factory takes energy and the transport takes energy. And that's another little bit scary thing. Now in Australia, you do a lot of mining, and that's great. There's sort of one of the biggest mining hubs of the world, and supplying raw materials to all the rest of the world. But for example, steel, I mean, in Europe, the European Union used to be sort of the steel and coal unit, or Union of Europe. It's where all the countries agreed on how can we exchange the coal and steel, because it's so important for our growth in Europe. But now, I mean, most of the steel we consume today come from Russia or China. China is actually, if I remember correctly, it's sort of 65% of all steel in the world. So for products, normally we say that China is the world's factory, and it's true. I mean, if you look at it, China produces roughly 1/3 of all products being consumed in the world. But remember that for steel, they actually produce 2/3 of all steel being consumed in the world. So, and similar with not as high percentage, but they also make lots of concrete and lots of aluminum and other important raw materials. And all of that takes energy. Anyways, getting back to the ammonia. So ammonia is important for growing food, but ammonia is also one of the best hydrogen carriers that we have, because basically ammonia is nitrogen from the air. The air around us is 80% nitrogen, and so we take the nitrogen out of the air, and then we make hydrogen, and then we can combine the two, and that is ammonia. So ammonia is NH3, and if you cool it down, then you have liquid ammonia, which you can transport in trucks and ships and other tankers. So it's very easy to transport around, whereas hydrogen is a gas, and it's super difficult to transport it either in tankers or pipelines. So normally, if you have to transport hydrogen, you would always convert it to ammonia and then transport it, and then you can convert it back into hydrogen at no cost, almost no cost. So ammonia is, in addition to being a fertilizer for food, that's the most important job for ammonia, but it's also one of the greatest ways to transport hydrogen. And hydrogen is, of course, used for all kinds of products, and especially if you don't want to use natural gas or oil for your product, the petrochemical industry, then, I mean, the only other option is hydrogen. And also, if you want to make green steel, for example, again, you need hydrogen. So hydrogen is going to be more and more important in the future, and we will see that in most cases it will be manufactured at an ammonia plant, and then the ammonia goes onto the global ammonia market. And some people will use it for fertilizer, some people will use it as a replacement fuel for diesel, because that's another thing about ammonia, is that you can actually, if you make minor changes on your diesel engine, then it can run on ammonia. So ammonia is also a liquid fuel for trucks and ships and mining equipment and trains and everything. You could even use it in airplanes, but there's a problem because ammonia is a little bit toxic. So if the airplane have to dump its fuel, then you dump a lot of toxic fuel. That's not too good. So I don't think we will see many airplanes with ammonia as a fuel. But anyway, so there's all these different uses for ammonia, and also a lot of places, especially in Japan, in order to make their gas-fired power plants and coal-fired power plants more green, they actually co-fire with ammonia. So for example, in Japan, they will have 50% coal and 50% ammonia, and then you could say the electricity is 50% green. So that's another use case. So there are so many use cases for ammonia and, of course, hydrogen. And therefore, in Copenhagen Atomics, we also believe that a very large percentage of the nuclear reactors we are going to build in the next 20, 30, 40 years are going to be used for making ammonia. Because ammonia is sort of basically it's a liquid storage medium. You store energy in a liquid form, and you can easily transport around. So it's a better way to store energy than in batteries, and it's almost as efficient as storing energy in diesel or gasoline.
Yeah, totally. Yeah, it's like I have electric everything, but I'm also still not a big fan of batteries and electricity being the number one solution because there is a lot of mining and energy that goes into all those resources, and it creates a lot of waste. And like cars as an example, I think we have cars, we have badly designed cities, that's where it all comes down to, is badly designed cities and things like that. So I'm a big fan of hydrogen. I think it could be a really good solution because, one of the big things with all the vehicles that we have on the road, and I actually was unaware you could use ammonia. I know big ships and stuff use it, but I thought, our cars we drive every single day. Like, I think if we had a fuel source that was made that we could reuse in diesel or petrol cars or like older cars that we've already got, there's a lot of save energy there just by not throwing them out and starting again, So I think it's, I know a lot of the race car teams around the world make some synthetic fuels, which are meant to be green and environmentally friendly. So I think, it's a good storage of, where in Australia, we have a problem with that. We have an abundance of solar power. In Australia, in the middle of the day on the wholesale market, we actually get paid to use energy. There's way too much solar that they're paying everyone to use energy because they're really fining the big energy producers for injecting into the grid. But as a consumer, you get paid to use that energy. And I've always thought that, hydrogen could be a good way of, in the middle of the day, we're dumping all that energy back into hydrogen getting made. When everyone leaves work, they go grab their hydrogen tanks, put in their car and drive home and, power your house on gas, hydrogen, at home and things like that. So, because that's all we're really trying to do is, transfer energy from one thing to another and finding out what's going to be the most, the smallest amount of energy we can put in to get the most energy back out. So, and I think that's probably a good way to talk about, tell us a bit more about uranium versus thorium. So what really got me excited about thorium a long time ago was a mate of mine sent me a thing about a thorium car that didn't need refueling for 100 years, and that's where I started looking into it and getting into it. And that's what I was like, I can just see that a tiny amount of energy can produce so much energy for a long time. So tell us a bit about, the benefits of using thorium rather than uranium.
Yeah, I just want to make a quick disclaimer because I've also seen all those stories on the internet with the thorium car and so on. From a mathematical standpoint, of course, it's true that if you calculate the amount of energy needed to move a car along, and then the amount of energy you could potentially get out of the fission of thorium, those stories are true, but they don't really explain how you would make that car. How in reality, would it be possible to actually construct a car? The thing is, you need sort of a quite big unit to make a reactor go critical. And there are some rules about, we're not allowed to use highly enriched uranium or highly enriched plutonium or stuff like that, because those materials could then be diverted to make bombs. So if the civil sector should use these materials, they have to be somewhat diluted. And I've never heard of anyone making a reactor core that is smaller than the one we have, with 5% enriched uranium, for example. And our reactor core is like 2 meters in diameter. And because we use these molten salts and you fill it up, the weight of it is almost 10 tons. So, I mean, that's not, and I don't see any way you can make that smaller if you want to use 5% enriched uranium. I mean, if you could use bomb material, of course you can make it smaller, but you're not allowed to do that. So I mean, how you couldn't have a car with that kind of reactor. And the next problem is that it's, those reactors give off a lot of radiation, both gamma radiation and neutron radiation, all kinds of radiations that would kill you instantly if you don't shield it somehow. And therefore, when you construct a reactor, there's all kinds of things around the core, like shielding and concrete and stuff. And you're not even allowed to have people in the building where it's running. So how do you put that in a car? Like you would need like a meter thick wall of lead between your driver's seat and the reactor, and that would also weigh like 10 tons or whatever. Yeah. So it's before you have something that can drive, it's bigger than a truck. And then still you're not really shielding the neighbor cars or whatever.
Damn, so someone's in a thorium car.
It's not really possible to construct that with the knowledge we have today. If you have to use those low enriched uranium, for example. But of course, it's a different story. If you can use bomb material, that is when you can make stuff like that. Or you could make a rocket or something, like a rocket that could fly into space or things like that. And there have been examples. I mean, in the past, if you go look on the internet, there was people in the US back in the 50s and 60s that built nuclear rockets where it was a nuclear reactor, basically heating up helium and spewing it out of the back, and that would make it into a rocket. But I mean, that's not really viable today. I mean, it's physically possible, but it's not something we could get approved today. Even back then, they were not super happy about improving or approving. So that's some of those stories about, and there's other stories about thorium on the internet where it says thorium can never be used for a bomb, which is sort of true, because thorium by itself, if you try to build a nuclear reactor and you only put thorium in there, it's impossible to start that reactor. It cannot. It's not possible. And therefore, of course, you can also not get it to explode like a bomb. No matter how you configure that thorium, it's impossible to make a bomb out of it. But of course, it's not the entire truth, because in a real nuclear reactor, you also have other materials like uranium or plutonium. And then suddenly the story is a little bit less simple. I would sort of turn that argument around and say that any type of machine that makes neutrons can also make bomb material. So any fusion reactor can make nuclear bomb material. Any reactor that we have in the world today could potentially make nuclear material. But of course, we've made rules, and they're built in a certain way that makes it really difficult to make bomb materials with those machines. And we've done that to such a success that no country has ever built a nuclear weapon from a civilian nuclear power station, because it's too difficult. It's much easier to build special purpose reactors that make bomb material. And I think that's the real story to tell here, is that nobody has never tried to make a nuclear bomb out of civil nuclear power plants. They all try to do it in a different way. And that's also true with fusion power plants or thorium power plants or molten salt reactors, no matter what kind of fuel they run on, is that, states would not try to make bombs in that way. But you can't say that it's entirely impossible, because they generate neutrons, and with neutrons you can make fissionable material. And it's not only just reactors and fusion reactors, it's also these linear accelerators that they have in CERN, for example. They also generate neutrons. So, but it's a good thing that we've never seen those machines being misused for weapons.
No, totally. So I think a lot of, it's just education and knowledge, and people just don't know all this stuff. So I think, a lot of the other oppositions of oil companies and gas companies over the years to stop another alternative. There's lots of marketing campaigns that go in to scaremonger the masses to say, like nuclear is banned in Australia. We can't actually produce anything from nuclear, any power. But like I said before, we've signed this deal with the states to take their submarine waste, or take the waste from the states and bury it here in Australia, which is a bit crazy. So, so what's the benefits over from thorium to uranium, using more thorium than uranium in a typical?
It's basically because of for example, for us, the way we have constructed our reactor, we can get this very, very high efficiency of the burn up. I told you early on that in most of the classical reactors, you unload the fuel when you burned only 2% of it.
Yeah.
And when you do the right mix of uranium and thorium, and in our case with this heavy water moderated reactor and the thorium blanket, you can burn almost 100% of the fuel. And therefore, of course, you can see from 2% to 100%, you can already see that that's a factor of 50 improvement in fuel burn up. But then also our reactor is much smaller than the per megawatt hour or whatever. Our reactor is much smaller than the classical nuclear reactor. So we also need less steel and less concrete to make the reactor. So it's just much more efficient. And this is how we get to this factor of 100 less mining per unit of energy produced.
Yeah. And real estate is to me, I think decentralized power is more efficient than, if I get in Australia, we have a lot of big solar farms and wind farms, and they're all built in the middle of nowhere. And then you've got a transmission lines to get into, so I think the smaller footprint we can have our power stations and have them put in more urban areas or closer to urban areas. It's one of the big reasons that they go west, because in Australia, they go west because the land's cheap. No one wants to live out there. No one wants to do anything else with it. So put a solar farm up or a wind farm. So.
But in terms of nuclear, if you want to sort of distribute nuclear, like let's say Australia, you wanted to have 10,000 different nuclear sites for every little city or whatever. I mean, the big cost there is, it's expensive to get approvals to make a new nuclear site. And of course, that's not a technical requirement. This is because of the way we've decided to run our society, that in every country I know about, it's super expensive to get the approvals to put up a nuclear power plant. So that's sort of, I mean, and it's not like that price scales linearly with the amount of power that the site produces. There's a startup cost that is already pretty high. So this means that you have to have those reactors at a certain size before you can even make them economical. And then if you double the amount of power being produced at the site, then you have twice as many megawatt hours to pay for that initial approval.
Yeah,
so therefore, there's a benefit to making bigger reactors, and there is a little bit of benefit in terms of the sort of the engineering and the materials you need, but mostly that benefit goes towards all these approvals, and also when you handle nuclear materials like we talked about before, you don't want anyone to steal those to use it for dirty bombs or nuclear bombs or whatever. So all nuclear power plants in the world have a very high safety level. I mean, most of them have armed guards and several layers of safety, and that also costs quite a bit of money. And I mean, you need the same amount of armed guards whether you have 100 megawatt power station or a 500 megawatt power station. So that also drives up the cost per megawatt hour if you have a very small unit. So that's why I think, I mean, for many years to come, we will see most of those units being quite big. I mean, when I say quite big, I mean a couple of 100 megawatts and upwards, so 2 gigawatts. I don't think there are companies trying to design what is called micro reactors. Micro reactors is sort of a 10, 20 megawatts, or maybe even smaller, like 500 kilowatts. Those are mostly for really special applications like on the moon or something in Antarctica or maybe a military base in some country where delivering diesel oil is super expensive, then it makes sense to put a microreactor. But I don't see how you could make a microreactor economic for a mining site or a small city somewhere that is away from the grid. I believe that wind and solar and just a diesel generator would be better in those sort of civil remote locations.
Situations,
But that's my opinion. I know other people have a little bit different opinion, and they think that we can work with the authorities and try to get the cost down. And of course, I mean, if the authorities and the legal framework and everything is going to change so that it will only cost you $10,000 to get an approval for a nuclear microreactor, then of course everything changes, because then maybe it is economic.
Yeah. No, totally good information. Thank you. So, because we actually have in Australia, we have a Lucas Heights. There's a nuclear reactor here, and a friend of mine actually worked there. So, so it's interesting. So we could maybe, so just on that, so, would it be possible to retrofit an old nuclear reactor with your technology?
No, not really. I mean, we sometimes talk about that you can reuse the site license, because when you get some kind of site approved for nuclear, you have to do a lot of environmental study to see if there's earthquakes or any endangers flowers or animals or stuff. And that costs a lot of money to get this environmental approval. And of course, that can be reused if you want to build a new type of reactor. So there is still some, it's better to go for an existing nuclear site. Also, another fun thing is that, now there's a number of nuclear reactors that has been decommissioned in Europe, and there's a lack of new nuclear sites available in Europe. So most of the time, people would try to build a new reactor at a site that has already been decommissioned. And the fun thing is that those people who lived next to a nuclear site in the past, they are much more welcoming to have a new reactor there than if you try to put it in some new location where the neighbors had never had nuclear power as a neighbor. So because those people have lived there for, 50 years, and there's never been any problem with the nuclear reactors that was there before, and it even created jobs and stuff. So usually it's much easier to get the approval at a site, at a previous used site, than to try to make a new site.
Yeah, cool. We might be able to get nuclear Lucas Heights going again here in Australia, and all this submarine waste is sending over from the States. We'll be able to, use your technology to burn it off and reuse it.
Yeah, I mean, we would love to buy that waste and use it. But I would say, though, there's something unique about submarine reactors, because it's a military application, so they have very different rules than for commercial ships or commercial nuclear reactors on land. So most nuclear submarines in the world are allowed to use these uranium fuels with much higher percentage of enrichment, which is not, normally it's not allowed in civil nuclear power plants. And this also means that the waste is more potent, and therefore you're probably not allowed to sell that waste to any civil nuclear power plants. You first have to downblend it or convert it to something less potent. But of course, that can be done. And I know they did that, for example, when Russia was converted from the Soviet Union to Russia, a lot of nuclear bombs was dismantled, and they were converted, downblended into sort of what is called MOX fuel for nuclear reactors. So we have done that before, and of course we can do that again. So I mean that fuel from those submarines can, but I also think if I remember correctly, those submarines are designed to run for 25 years without replacing the fuel. And this is back to that story from the beginning, where civil nuclear power plants, they have to replace the fuel every 2 years or so, because they can only burn 2%. But in those submarine reactors, you can burn maybe almost half of it. So they can run for 25 years before they have to replace the fuel. And then once you replace it, there's still there's still a lot of energy in that fuel. It's not waste, and that's why I say we would be happy to buy it, because we could mix that with thorium and make more energy out of it. But there's that little story that we probably need some kind of national lab or something in between to handle that, because we cannot get it directly out of the submarine. That would probably be illegal.
Yeah, I think as a society, it's something that we're better at is using things that still have potential energy in them and reusing them. You know, that's sort of the we just live in a throwaway world. And you know, as an example here, we just had a major flood through our town almost about 2 years ago, and so many things were just thrown out that could have been reused or redone again. Like a lot of fridges and freezers, and you know, you could have just been hosed out. They're all switched off. So when the power was turned off at the town when the flood hit, so all these devices, there's nothing wrong with them, but they all end up in landfill because people didn't want to wash them out. You know, so I think a lot of that goes on in society from a small level to a big level of so much potential energy that we have. You know, nuclear waste, where you guys have created a product to reuse that waste and get more energy out of that before it just goes into the ground for 100,000 years, you know?
Yeah.
So looking more
that it would be a really, really bad idea to put all that they call nuclear waste in deep geological storage, because eventually it's going to be worth more than gold and diamonds, you know, the same weight than gold and diamonds. It's very, very valuable material, and definitely we should not. I even think that, you know, some countries are probably going to put it in deep geological storage. The great thing about that is that we know exactly where it is. So later on, it will be cheaper to dig it up again than to mine for new materials in new place. Because when you mine for new materials, you have to search. You don't know exactly where it is. But this nuclear waste, we know exactly where it is. So it'd be much cheaper to dig it up again than to
X marks the spot.
Yeah, exactly. I mean, but maybe in 100 years, 200 years from now, they will definitely dig that up again.
Totally. So it might be for the future generations. It might be the new mining for the future generations, because we've run out of other stuff to mine. So
maybe.
So awesome, well, mate. Thank you. Is there anything else you'd like to add?
No, but it was great talking to you and having a conversation about these different things.
No, really enjoyed it. So thank you. So we'll put all your I'll get all your links to the best place for people to contact and follow you guys. And I know I've watched a lot of your YouTube videos and really interested. So we'll put those in the post below for anyone at home that wants to follow and listen and learn about Copenhagen Atomics. So, mate, thank you. And next time, have a great day.
You too. Bye-bye.
I hope you enjoyed this episode and found the content educational and inspiring. If you got something out of it and you think you know someone else that would actually also enjoy it, we'd really appreciate if you could share the link with them and encourage them to check out our channel. And don't forget, you can join the Off Grid Tribe podcast for free, where you can actually ask and interact with myself and also our guest speakers. So jump over today to offgridtribe.com, register yourself an account where you can actually have a conversation with myself and one of our guest speakers, and we can continue the conversation there. Together, let's embrace the power of sustainable living.